So, the amplifier that we're going to be looking at tonight is a 10,000 watt amplifier, and it is by the brand of Vibe, which is a British audio brand. You might have seen in Exo's videos a few Vibe stuff, but they have made, or they have put their name on some pretty decent stuff. So this is a 10,000 watt amplifier. I think it's a Korean build. It is based on very old circuit architecture. It's the same as like a Ground Zero 10K HC or Sundown NS1 is the same circuit architecture. It's all the same drive circuit, it's all the same outputs, it's the same everything. It's just a really old, big, beefy. It's like, think of this as the old American muscle car of car audio amplifiers, and the Brazilian stuff is like the Japanese tuner style, I guess. That's kind of one way of looking at it. Yeah, so this amplifier is quite handy because it comes apart in two parts. So we've got the power supply section here, over here, and then the output section does this. So we can get rid of the output section and isolate and work on the power supply section, which is kind of useful because it's such a large amplifier. And this amp, the power supply section is dead as fuck, and the output section is dead as fuck. Like, so this is the output section board. I'll show you, there's a board over here. This is the output section board, and we're missing the driver board, so I've asked the customer where the hell that is, because obviously we need that to start working on a repair for this section. We have got over here, there's some little small transistors just by the driver board. These are snapped off, so they're probably dead, or they just had a poor repair. We've got missing output FETs. It's all pretty bent. We've got missing pads on the driver board where it's been ripped out and not been desoldered properly. The power supply section is blackened. We've got lots of blackened FETs here where they have smoked up and let out the magic smoke. So yeah, as we discovered earlier, we've got 36 064N MOSFETs to replace on the output section. And this is my current inventory of 064Ns. So for today's live stream, we will be putting one FET per bank to get this up and running and to continue with our repair. And once the repair is finalized, we will hopefully the replacement, the rest of these 064Ns will have arrived in the post. This is a fun one to look at. Bye bye. Bye bye front of FET. So what do you reckon? Do you think this one's dead, guys? I'm going to start snapping some of these blatantly dead FETs off the board, and then measure the resistance between the positive and negative terminals. And at some point we'll get to the point where we no longer have a short circuit on there. Yes, Chevys not Hondas. This is a big amplifier. This is a big old-fashioned amplifier. That is very true. That's actually a really good little observation there. The more you flex the legs, the higher impedance it's going to have. Indeed. So, all of these output FETs, all of these power supply MOSFETs are being driven by these 8 drivers here. Now let's see, are these being run in a PNP NPN format or just PNP? So we have an A and a C, so they're PNP and NPNs. Now I don't know if you can see, look at that one. This driver has also exploded in a similar way to the output MOSFETs. Damn, the chat is going crazy this evening. I can't keep up with the chat. Okay, that's all our drivers removed. Removed. Let's get rid of all that carbonized nonsense. Damn, look at the state of that toothbrush now. Now we can put some power into this board and we can see what the drive waves look like. So this is a very, very standard board here. Let's zoom in for you, so you guys can see. Where's my camera zoomed into? There we are, there we are. So, does anybody recognise that? So this is a very standard power supply. This has a KIA, a Kia 494AP, which is the same as a TL494. So this is the chip that generates the pulse width modulated waveforms for the power supply to work with. It has a sawtooth wave on pin 5, and it has VCC on pin 12, and it has a out of phase square wave, two out of phase square waves with each other on pins 9 and 10. So this is what we need to look at to make sure that this thing works. We need to check the square waves on pins 9 and 10 and make sure they are good. This then sends its square waves on pins 9 and 10, its pulse width modulated waves. It then sends them to this bank of driver transistors, which we can see if we move that wire out of the way. So this bank of pads here had driver transistors on them, NPN and PNP, and they buffer this switching drive wave before sending it all the way over here to all of the power supply MOSFETs. So let's hook up our very small power supply. This is our 9 volt power supply, 9.8 volts technically, because we don't want to put too high voltage into the amplifier whilst we're just testing it and playing around with it. 9.8 volts is very safe. Although, as I learned in my last live stream, or one of my last live streams, with the B2 audio, the Duo Mark II doesn't power up with 9.8 volts. Now, 99% of other car amplifiers do power up on 9.8 volts, but the Duo Mark II does not. So we're going to start looking at whether the 494 chip survived. I think it probably did. So 494 chip is just situated in here. That's the transformer. 494 chip. This is the chip which may or may not have died because we had some nasty blown driver transistors here. So if they blew in a bad way, which they did, it may have pulled the 494 down with it. So let's check that out. I'm going to apply some power now to this board. I'm going to see what the wave looks like. Power supplies are generally quite easy to repair. They should be simple to repair. I emphasize should be. Okay, so we have our 9 volts sitting there ready to go. Let's turn my scope on so you guys can see that. So yeah, we have our 9 volts there sitting on the middle pads of all these MOSFET pads here. So this is the power supply section. So we always have our 12 volts, or in this case our 9 volts, because we're using a 9 volt supply, on the center pin of these MOSFET pads. And this is how the power supply section works. So what we need to do is we want to see whether the drive wave coming from the TL494 in the middle here survived. So if I zoom in again to the 494 chip, and I'm just going to probe pins 9 and 10 and also pin 5 and make sure the chip is healthy. So if we look along here, we've got pins 9 and 10 over here. So let's apply our remote, and we can see here, if I turn to reject low frequency, there we go. There is our drive wave on. That's pin number 9, and that's pin number 10. So yeah, the chip seems to have survived. Let's check the sawtooth wave on pin 5. That's the operational sawtooth wave that this chip operates on. Let's zoom into our scope so you can see that. So if you're ever looking at a 494 chip and you're wondering whether it's operational or not, whether it's working, you need to make sure you have this nice looking sawtooth wave on pin 5, which is also why you need a scope for amplifier repair. It's very important. This chip also has a very accurate 5 volt regulator built in. So if you have 5 volts on, I can't remember which pin it is. If you have 5 volts on pin 11, 12, 13, yeah, if you have exactly 5 volts on pin 13, this chip is also operating correctly. And you should also have a nice looking square wave, like so, on pin 9, and a nice looking square wave on pin 10. So we can also just check that the trace isn't broken to the buffer transistor section here, just above. So we should see the wave appear on this pin here of the PNP. And this pin here of the NPN, PNP, NPN, and the same over this side, PNP, NPN, PNP, NPN. So the chip survived. That's good news. So what we can do next is we can load up some fresh drivers into this bank in the middle here, and make sure that the pathway from the drivers to the outside of the board where the MOSFETs are fitted is clean. We might have to change some gate resistors. Gate resistors are in between the MOSFET gate and the driver. I think they're probably going to be a 22 ohm. Different manufacturers of amplifiers use different ohms on the gate resistors. They can be 47 ohm, 10 ohm, 22 ohm. So Vibe decided to use 47 ohms here, which is different to the one we saw the other day. I was repairing a solid the other day which used 22 ohms, didn't it? So we have 47 ohms gate resistors on this amplifier. Okay, let's get some new drivers for the SEM. So go to my little drawer here. We have my drivers. Now for replacement driver transistors here, we have a few options. Many guys will tell you to use BD139 and BD140 driver transistors to replace the originals with. I have used those with good success, but I have also had even better success with using BD139 as the NPN, which is absolutely fine, but the one which is important, the transistor which needs to be quick in pulling the drive down, is the NPN. And so rather than using the BD140, which isn't that great, we can use a B772, which is pretty much the same thing, but it's just a little bit better than the BD140. So this is a B772, or B772-Y in this case. So let's get 4 of those out, and I just need to suck the solder from those holes in there of the original drivers, and then we can load these new drivers up and make sure the gate resistors are okay, which they probably won't be because this power supply went down in a pretty bad way. So, are all new brand amps using SMD technology? No, they're not. Not all of them are. Xenon factory in Korea are still making amplifiers with through-hole circuitry. I imagine it probably is. Okay, so we are fitting some new driver transistors now. So I've got my my NPN and my PNP driver transistors. We've got our B772 PNP. So that's going to go from memory in the right locations on the board. This is so disorientating, this camera thing. There it is. There we go. So we're going to load up our PNPs in here. And we're going to take another PNP. Load her up here. Third PNP. That's not a PNP, that's an NPN. So let's put one NPN in here, because I just picked out an NPN by accident. And that's another NPN. How well does this camera show up? This camera is connected to the world's cheapest HDMI capture card, but it actually has less lag than my expensive Hauppauge Colossus 2 capture card. The Colossus 2 has horrific lag. This is another PNP, so let's put our 4th PNP in place. Because I'm a motherfucking PNP. I don't know what you heard about me. And now I need to find 2 more NPNs. There's one. It's so much nicer to be using a small pointy tip rather than having to get my great big wedge tip in here. So much nicer. So first of all, I'm going to probe the TL494 because I wonder whether I just killed it by sparking the board up with the power supply still connected. So pin 9 looks good, pin 10 looks good, so the 494 is fine. So if we go along and look at the drive on some of these gate pads for the MOSFETs on the power supply section, let's do the first bank. So the first bank, that's not present. No square waves present on the first bank. See that? All we have is this nasty looking attempt at a square wave. So I imagine that there's an issue with the gate resistor. Nope, it's probably the pull down resistor, because if we I've just probed before the gate and it's not there either. So we have an issue with the pull down resistor on this first bank over here. Let's go along and try some of the other banks. No good. No good. Doesn't look like we have drive anywhere on this board. Nope. No drive. No drive anywhere on this board. I wonder whether the markings are the wrong way around on this board for these drivers. I had that issue with a sundown amplifier that I was working on before. So the markings on this board tell you which way round the drivers should go, the transistors. It has a flat edge and it has a chamfered edge sides. And that tells you which way round they should go. Just flipping over these drivers, changing their orientation because I got trolled by the board markings. Okay, that should work now, fingers crossed. 9 volts, drive, yay! My bad! Drivers were flipped around the wrong way because the board markings are strange on these. They're backwards to how they usually are. So we've got drive on all of these banks here. All these banks are looking identical with the drive waves. Yep. Okay, cool. So the drive looks good. Now because this power supply went down in such a bad way, we might have some gate resistors that are out of tolerance. So what I want to do is I'm going to go and turn my multimeter to ohm setting, and we need to check all of the gate resistors to make sure that they are all measuring around about 47 ohms. We can see 46 or 48. That is our tolerance range we're going to go by. So let's check number one. This is a lengthy ass process. This is kind of annoying. Checking every single flipping one. 45 ohms. That's a little bit lower than we need, so we might need to replace that one. I might just replace all of them. It's a bit long because I've got so many here. I don't really want to have to replace them all if I can get away with it. But this one is 46.3. To be fair, they'll still work fine, to be honest. 42. So every single one of these has a pad. So yeah, actually looks like this bank over here that didn't get mutilated, that didn't get smoked up, are all measuring 47, you see? So I can get away with not replacing any of them on this bank. However, the bank that is next along did get hurt, and we probably have, that one's 45. So from here onwards, we need to replace them, and that's probably a different bank. I'm using my Dell power supplies to power my vape because my batteries run out and they won't charge. Okay, so we needed to remove these ones over here and these ones at the end. So let's start pulling these gate resistors up off the board. With the gate resistors, you can use a resistor which is of the same size as the original or bigger. You can use a bigger gate resistor, a bigger power handling gate resistor, and it's fine. What if I could manage to learn amplifiers from YouTube and Beveridge? Yeah, you probably could, Jos Zane. You probably could. Okay, drive waves look mainly good, look pretty good. Yeah, they're all the same and equal. All the same and equal. Okay, fantastic work. So we're ready now to fit some power supply MOSFETs in place. So we're going to fit one per bank. If you weren't watching from earlier, we have 6 transformers. We have 2 banks per side, 2 drive banks per side. There's 4 pairs of driver transistors in the middle of the board here. So we technically only have 4 banks in this amplifier, but we have 6 transformers. So the banks, the two banks either side are split up into 3. So we have 1, 2, 3 high side, 1, 2, 3 low side. So we need to fit 1, 2, 3, 4, 5, 6 FETs per side because we need 2 FETs to run each transformer, 1 to push, 1 to pull. Thank you very much. So we're going to apply some, going to fit some power supply FETs. Now this amplifier needs 36064 ends. I only have a small handful here, literally a small handful. So we can't fit them all into this amplifier, but we can get it up and running with the bare minimum. So I need 6 per side, so I need 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. and I have 3 left, so I only just about have enough to run this amplifier with the bare minimum. The floor 8 one. Ah, yeah, the floor 8 one earlier, didn't it? There it is. Here's the one that the floor 8. I forgot the floor 8 one. So we've got 9 volts sitting there on our MOSFET. So before we apply any power to this, we want to just make sure that the pads are all in good condition, and we have our 12 volts, or in this case our 9 volts, going to each of these FETs. So we want to just take the multimeter probe and just make sure that we have 12 volts, or 9 volts in our case, on each one of these FETs, because if it's missing from any of these, then we can blow the FET, or we can blow the other FETs. I just want to make sure that we have 9 volts on every single one of these. Yes, we do, sir. Okay, now let's apply the remote and let's see if the thing powers up. Charging rail capacitors, can you see that? Charging, charging, it's getting closer, it's getting closer. Yeah, boy! Da, 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 da. I'm just going to see whether these are heating up at all. So we've been running those FETs now. So one of the FETs over here is getting a little bit warm. I'm going to compare the drive wave on all of the gates of the FETs that we've added to see whether it is equal, whether it's uniform across the board. So we've got this one here, which seems to be getting a little bit warm perhaps. Let's pause the scope on that one. And let's jump over to this other one over... Wait, what the fuck? Let's jump over to this one and let's just compare that wave of this one over here. So let's pause on the scope and jump over to here. Okay, so that looks pretty much the same. Very slight shift in how it looks. You can see there that the top of the wave here... Whoa! Something went ptss on the board. Something went ptss. So none of the FETs... these ones feel a bit hot. These ones feel a bit hot. So we've got cold, 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 hot, lukewarm, cold, cold, hot, lukewarm, cold. So something went on the board. I'm going to go along each of the other banks and see whether we have a volt on any of the other banks. Oh wow, holy crap. We've got 9 volts on the gate of this one. Holy crap, okay. So yeah, this is where the issue is. So you see this one here, this single FET here on the gate has a full 9 volts coming from the power supply. So there's a short between the gate and the... that's getting very hot actually. I need to remove that power supply. Let's pull the FET off the board and see if the short circuit goes away. Okay, so let's apply the power again and let's see whether we still get 9 volts on that gate. Interesting, we don't get 9 volts on the gate, so does that mean that this FET is dead? This FET is one that I had previously installed on an amplifier before actually, so it could just be that this one's dead. Let's just check with our multimeter. Yep, this FET's dead. This could have been a duff one. I thought all these new ones were good, but perhaps not. Ever had a transformer cause a short? Yes, transformers are a nightmare with shorts. They can short all the time. And it's due to vibration damage, due to a poor build quality of the amplifier. Okay, that's that one replaced. So let's apply the power again. So I'm gonna start off probing over this side because this is where the issues were just a moment ago. Okay. That looks more healthy. That looks more healthy. Let's just check this one. This one was failing before. That looks about the same. That looks about the same. That looks about the same. So I think I must have just accidentally put a dead FET in. I didn't realise was dead. No worries. But let's power her up fully, full duty cycle. Da, 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 da. Okay, now let's check these drive waves. So we're going to stop, pause. This one's a little bit... You see how this one's a lower amplitude than this one? That's not good. So we have an issue then with this bank. This bank, the amplitude is too low for that drive wave. That drive wave is too low. Let's see what this one's like. So I'm going to pause the scope again on this one. Pause, start. Okay, that's too low. Pause, start, too low. We might have damaged the driver. Pause, start, too low. We might have damaged the driver with that dead FET, so we can pull and change the driver for this bank. I'm just going to wait because this rail voltage needs to sink down because this is way up higher. What is the rail voltage, just out of interest? So with 9 volts worth of input, 9.8 volts worth of input, we have 111 volts on the plus and 108 volts on the minus. So we've got a slight difference in the rails there. We need to look into that. But yeah, so if I was to put my 2 fingers on these 2 terminals here, then the potential difference between those 2 pads is 220 volts DC, and that would probably blow my fingers off. Because when they see like a 3-hour video, I know a lot of people get put off and they're like, hell, I ain't got time to watch that. It's the same. So they're probably fine. So we might have some other issue on the board then. I'm going to replace them anyway. I'm going to swap them out anyway. Power. Get those damn rail caps charged up again. The audio has been pretty clean on this stream, isn't it? It's not crackled like last time. Okay, check drive. Compare drive. That's the same amplitude. Next one, that's the same amplitude. Next one, that's the same amplitude. Next one, that's the same amplitude. Next, I think we're good. I think we're good. I think it was the drivers, even though they didn't show up as bad on the transistor test. I think they were bad. Yes! Yeah, boy! What's up? So now we have equal drive on all of these gates. They should be staying pretty cool. They should be staying pretty cool. So we're going to whack out our... what we want to do is we just want to make sure that they're all heating up in a uniform fashion. And by that I mean they should all be reaching the same temperature. If we've got some banks that are heating up considerably more than others, then we have something we need to look at. So, FET number 1 is running at 30 degrees. Getting slowly hotter. 31. FET number 2 is running at 31. FET number 3 is running at 30.5, 31.3 now. This one here is... see, this one here is 38. This one here is quite a lot. That's up to 40 degrees. Now that is not good. I don't like that. This one here is 31. So why are you heating up more than the rest of them, my friend? You're up at 40 degrees. 35. So, okay, so they're all around the 30s, but we've got one over here that's a little bit hotter, up at 40. So I'm going to take my hand. Oh yeah, see, that's actually quite hot to the touch. I know why it's getting hot. Duh. This one is batch B8V5, and this one is batch completely different, G38T. So it looks like that I thought that my drawer was full of ones of the same batch, but it wasn't. So that just goes to show you that because we have 2 different batches driving the same transformer, it can cause heating issues, which is why it's so important to run the same batch on each transformer. The 9.9 degrees. So they're all reaching at or around about 38 to 40 degrees. So if we had any issues with the power supply section, that was due to drive on one of the banks or a couple of the banks, then they would be heating up differently, like they were a minute ago when we had this one FET, which was getting too hot for me to hold like this, because we had a different batch number from the factory of FET in this transformer. My mistake. Okay, stanky ass output section board. What are you saying, bruv? What are you saying? So let's see whether we have any short circuits on this piece of crap to start with. We're looking for beeps. We're searching for beeps. Shh. No beep. No beep on any of these banks. Okay, no beep, but that's obviously not working. So we should have, when we measure between some of these pins, we should have charging. Okay, see, this is interesting, right? So something to note about the output section of amplifiers, with the driver board removed here, you should have absolutely nothing on the multimeter screen on diode setting when you probe between legs 1 and 3 of these FETs, because probing legs 1, you're probing the drive circuit, which is not there, and 3 is kind of your virtual ground, so you should have nothing on the screen when you probe 1 and 3. If you do have something on the screen when you probe 1 and 3, then you have a short circuit, or you have a dead part. So you see this one here, we've got 213 on the screen here between 1 and 3, so this one is dead, so we need to get rid of that. Let's just check it still has that same resistance outside of circuit. Yes, it does. We still have that 200 ohms outside of circuit. So that one is stanky dead. Okay, so yeah, there was something else in the box that I hadn't seen. So in the box of the amplifier box, I found a packet here with some new driver boards in it, a schematic, and annoyingly, a little blown capacitor. Where the fuck did that come from? That's not useful. How useful is that? There's this little capacitor rolling around in the box, and I've got to try and find where the hell that fell off the board from. Here, these last transformers here have some smaller taps coming off them, which go into rectifier diodes here. Aha! I found the missing capacitor. Stevie G was right. There are four rectifier diodes here coming off of this transformer. And these are dealing with the plus and minus 18 volts AC, which then get rectified into plus and minus 15 volts DC, and that is then used for some of the OP amps around the input section and for the driver board. And there is a smoothing capacitor here, which is what that 35 volt capacitor would have been for. Look at this. I mean, what is that? That has less components in it than a head unit. This consists of, the power supply input here. Okay, the scope's in the way. Power supply input here. Okay. I don't even know where the FET is, where the switching FET is for that. But we have a transformer here, tiny ass little transformer, and then we have the output. This is a Class D or Class AB or Class D amplifier in one chip. So all of this is just wasted space to make it look big. You can always use a larger cap, not a smaller one. Yes, I can, but I haven't found anything larger than 100 microfarads yet. Ah, here we go. 35 volt, 220 UF. So that's a little bit bigger, but this is a smoothing cap, so that's ideal. That's not a problem. That will actually be better performing. I like literally a bit of everything. Heavy metal, I like some punk stuff. I listen to jazz music at dinner time and in the car sometimes. I listen to drum and bass, I listen to jump up, dubstep. Like, the only thing I would never fucking listen to is Gabba. I am never listening to Gabba. Right, let's start work on the output section then. So the first thing we needed to do was take these small transistors off here and work out what they are and replace them. I'm gonna wiggle this leg off because this is pretty much snapped already anyway. This is an NPN. As you can see on my transistor tester, this is healthy. So no, this one's dead. This one's dead, guys. This is only showing a diode between 2 and 3. Okay, here we go. NPN, which matches up with what we had earlier. So this is a 25 volt collector base. Collector emitter is 20 volts. And it is a 0.5 amp. Let's have a look at my drawers then, and let's see what small transistors we've got that would fit the bill to fit in place of this. So we need a 25 volt, 0.5 amp. Carlos says 139 will fit. Okay, wicked. We'll give that a go then. The making of Basshead Anthem. 25 hertz, 8 cubes, 1 ohm. Watch your screens on your dash as you're sitting on your throne for 100 amps from the cell, running through a zero gauge in-car entertainment like you're in a nice age. So the thing that I suggest that we look out for, this is where the driver board is. Okay, these are the 2 transistors I've just repaired. Now you see these little green things on the board here, these little green components, these are inductors. So they're tiny winds of copper coil. These should read about 5 ohms, or sometimes they're in 2 in parallel with each other, so they should read about 2 ohms, 2.5 ohms, and sometimes these will die. They will either go completely short or they'll go open. So what we need to do is measure those with our multimeter and make sure that they read about 5 ohms. If they don't read about 5 ohms, or if they don't read 2 ohms, if there's 2 in parallel, then we have an issue and you should change them. You don't need a lot of watts to get loud, get loud. You don't need to pay out to get low, get low. If you love your bass, you like time and space, it's by the bucks. It's by the bucks. That was a stupid ass song. Why did I ever make that? So back to the repair. So yes, sorry. Let's plug this board back into the main one, and what we're going to do now is we're going to jump over the rail connectors. So we're going to give the output board the full rail voltage of 100 and roughly 115 volts plus and minus. See how she likes that. 52, 54, 62, 69. It's getting there. It's slowly, catchy monkey charging these capacitors. 100 volts. Okay, the relays have clicked in, guys. Whoa! Woo-hoo-hoo! Poof! Poof! A shame I didn't have the camera on there. Damn, son! So we lost a cap. We lost a small cap that went boff right by the fan. So why did that go? What's that to do with? What is that cap to do with, I wonder? What we can do is we can remove both of those caps on both sides and measure the voltage around them to see why it wasn't happy. 25 volt, 220 UF. So the only reason that this would have died, this is 25 volt cap, if one of those voltages dropped off, then the cap will have blown because it's only 25 volt. And so we saw, I think, rail voltage either side of those. So if one of those voltages dropped off suddenly for any reason, due to any fault on the board anywhere, then that's why that would have blown. So okay, let's put some power back into this thing. Rail voltage plus 12 volts. So we did see that on the top of the board. So that's correct. And this should actually be present on both top and bottom of the board. So because the veer is damaged, it's not present on the bottom of the board. You see there how we've got 94 volts down at the bottom when I push my probe in. That should also be present on the bottom of the board because it's meant to make a connection through, but it's not because the veer is damaged. So this is going to skew our results. The next two ones are rail, that's correct, that's 6 and 7. So 8 should be rail plus 12 volts, again. Which it's not because the veer is missing, so that's why we were missing rail plus 12 volts down there. I think we potentially have all the rail voltages that we need to progress with this amplifier, and put the driver board in. Because the reason that we don't see some of the rail voltages on either side of the board is because the vias are so damaged. So the vias need to be in place for this thing to actually take the voltages where it needs to go along the board, because some of the voltages go through the vias. They're essential. Capacitor blew off. So I replaced the drive ICs on here, and I also replaced the diodes and a couple of the capacitors which read wrong. So it's easy to check the diodes and the capacitors, and a couple of them were reading funny, and I thought it was a good idea just to change all the drive ICs anyway. This is the original driver board. I actually have a spare driver board I got with this amplifier. The guy who sent it to me for repair, he gave me obviously the driver board that was in the amplifier and 2 brand new ones. So just for the case of the live stream, I was attempting to repair the original one just to show you how to repair it. So I changed all 4 of these original drive ICs, which we can see here if I skip onto the video a little bit. So yeah, it's all hot air, and literally, yeah, just refresh all the solder pads and then just drop the IC on like so. You can go ahead and do all 4 of those. You see all of these black things here, I decided to take them all off because I wanted to be able to solder the board to the top and bottom of the main PCB so that I could get all the traces that had lost their vias. So I went ahead and spent ages and ages removing all those black plastic things, which took me a long time. Once I did that, you can see that the driver board now looks like this. And I could then solder it from the top and bottom of the board onto the metal, the wires there. So that's me soldering it onto the board. And then once I had soldered that to the board, I put the rest of the amplifier back together, so redoing up the screws, etc., ready to apply some power to the output section to apply the power supply board to the output section board. I'm just doing some final diode mode checks and readings on the FETs to make sure that they are all good and none of the drive circuit is faulty. Then something really weird happened. I discovered that I had some weird resistances between the gate and the source of some of the FETs. And so I went around looking for ages what the hell the problem was. I tried changing the FETs again, and then I got to the point where I was like, fuck, we have to remove the driver board. So I had to remove the driver board again, and so after removing the driver board and not actually finding anything wrong on there, and the resistance was still present on the board with the driver board removed, which means that the issue was on the main board. So in a last final attempt to find out what the hell was causing this resistance between the gate and the source with the driver board out the board, there was a problem with the main board, I decided, what the hell, let's just clean off any remaining solder flux that's on the bottom of these pads. There were no solder bridges for absolute sure. The pads are quite far away from each other and it's very obvious to see if any solder bridges, and the resistance was up in the kilo ohms as well. So I was like, okay, screw this, let's just clean the board just for good measure and see if that resolves it. And lo and behold, cleaning the flipping solder flux off the board got rid of my weird resistance. So it turns out that the solder flux that I decided to use, that I bought, actually goes somewhat conductive when it's hot after it's been heated. So I won't be using that anymore. So that caused some bullshit issues, and that was probably a good hour and a half worth of troubleshooting to try and find where the resistance was coming from. Never in a million years did I think it was going to be coming from the solder flux. So after cleaning this off, yeah, I actually removed the resistance, and I went ahead to reassemble the board, put the driver board back in, and yeah, we're screwing the board back in together now. Then, once the board was assembled, I started applying some power to the board so that we could build the rail voltages and make sure that the rail voltages were where they should be on the FETs, and we're going to build the drive wave shortly and see whether it works. 83, 88, 80, 92, 93, 94, 99. We've got a green light. We've got a green light on the amplifier, but we've got no switching. We've got a green light on the amplifier, but we've got no switching. A couple of things happened next. I noticed that one of the FETs along the row that I left in the board that it came with, that I didn't decide to take out because none of them measured short, was heating up. And in hindsight, I mean, this video is actually quite old. This was back in February that I streamed this, and I'm a bit more experienced now. In hindsight, I should have just removed all of those, because some FETs can actually be damaged but not show a short circuit, which was the case here. One of the FETs was just now a diode and was no longer a FET, therefore it was heating up. And something else happened as well. The amplifier clicked into protection, so there was an issue that we needed to look for. I then decided to start probing the pins on the driver board to make sure the driver board was receiving all of the correct voltages it requires to turn on and also to start powering the FETs with drive. So went along and checked it had all the plus 12, minus 12, plus 5, minus 5, etc. and plus 15. And I came across the modulation pin, the modulator output pin, which is before the driver ICs. It's just from the Class D modulator IC, and that actually had some drive on it. So therefore I knew that the driver board was starting to kind of work, but the driver ICs themselves weren't turning on. But the actual Class D modulation circuit with the small ICs, TL027, was at 072, sorry, was actually turning on and outputting some waves. Then we move on to the next day, and I decided to have a pizza first. Now, I assumed that the issues I was having was as a result of the original driver board still having problems that I hadn't found yet. So what I did is the new headers arrived, so I soldered the pins for the headers first to the top and bottom of the board. Then I slid the black plastic part of the header over the pins after they'd been soldered to top and bottom of board, so that then I could run the driver board straight into the headers and make a very solid connection to top and bottom of board and be able to chop and change the driver boards in and out. So with the brand new driver board fitted, the rails are building, and we have switching waves. So there must have still been some slight issue on the original driver board that I had missed or something. This was back in February, so I cannot really remember. But yeah, we had switching now, and the output section started to work and come alive. So I'm just doing a little bit of more testing now, leaving the amplifier turned on for a bit longer and increasing the input voltage to make sure that the amplifier stays good. Switching! Switching! Woohoo! And the relay clicks in and it stays on. It stays on, guys. It does not turn itself off. So let's do that again. Whoa! Pooh! Woohoo! So once you've had something explode on the board, it's always a good idea to check your drive waves again to make sure the drive circuit didn't get damaged from whatever exploded and shorted. So here I am just checking the rail voltages and making sure that the drive is still present on all of the gates. And there we go, you can see the drive is looking really good on all the gates. So yeah, the drive circuit survived, it didn't kill the drive from that FET exploding. And that was because the FET just exploded, it just shorted the drain and the source together and didn't really affect the gate because it was just a diode and the gate probably got taken out already. So now I was very confident, we've got a brand new driver board, and I was saying to everyone, right, we're going to put this to one side for a while. I'm going to order the rest of the power supply FETs and all fresh output FETs so that we load this amplifier up fully with every single FET that it needs, and then we'll run one final test to make sure there's no other issues with this. So here's the rest of the video. I didn't live stream this bit, but this is the test with all the FETs in the board. Wow, okay, this is the moment of absolute truth, and I am very nervous at this point because this is a lot of money that could be wasted if there's something not quite right here. So we have fitted all of the power supply FETs in the board now. So this is, what's this, 4, 8, 12, 16, 17, 18, that is 36 IRF 064Ns fresh in the board, all the same batch, and there is 4, 8, 12, 16, there's 32 brand new 24 NF50. So these are the 500 volt parts, 24 amps each. And we're going to power this up fully now with everything fitted, driver board fitted. So this is the final stage of the repair, where we power her up and we see whether we get any drive waves, if anything heats up, if anything explodes. My luck hasn't been brilliant the last few times I've been powering up these great big amplifiers. Ground 010K keeps exploding FETs. So without further ado, let's power this thing up. And I don't really know what view to give you. I guess I could give you this view, or I could give you the scope view. That might be a nicer view for you guys, but if something explodes, then that view is the better one. So I'm just going to pulse the remote so we can see there on the scope, the rail there is building. So we've got 39 volts now on the rail. Maybe this is a better view. So this is the rail, this is the negative rail I've got probed. The other line, which is sitting at ground, that is going to be the high side drive. So when this amplifier comes into operation, we're going to see a nice big square wave on there. Okay, let's go again. So we're now at 52 volts, and I'm only giving this amplifier, like you can see here, 9.5. I'm going to go down to 9 actually. I'm going to go down even further to lower the rail voltage that this amplifier is going to see. It makes things a bit safer. Okay, so let's keep going. A little bit more. Okay, and we're now at 64 volts on the rail, so let's keep going. Whew, okay, a little bit of switching and nothing explodes, so that's a good sign. Okay, so we had a split second of switching there, so I'm going to go around and feel all these FETs, make sure that nothing is heating up, because a tiny little bit of switch like that can cause FETs to heat up if they're not happy. Nope, they seem good. So I'm going to let that on for a little bit longer and monitor the current draw in the amplifier. Okay, we got 5 point something amps worth of current draw there. And once again, let's go around and feel all the FETs. No, they're staying dead stone cold, and that should be the case with only 5 amps worth of draw. That's very good. For an amplifier this size, that's very good indeed. Right, go a bit longer this time. Okay, yep, looks good. 6.8 volts, 6.8 amps. Amplifier's clicked into operation. Looks good to me. The drive waves look incredibly nice. And turn her off, and nothing explodes when we remove the remote. And check once again for heat. I'm making sure not to touch anything on the ground because there's quite a high voltage on here that I'm touching, almost up at 100 volts DC. So I'm touching 100 volts DC right now, but because I'm not grounded, I don't feel anything. Yeah, that feels nice to me. That feels pretty good. Nothing's heating up again, so I'm going to leave it on for a little bit longer this time. You're just got to keep doing this until you're happy that the thing is stable. So 6.5 amps. Yeah, amplifier clicks into operation. We've got a green light on the board. I'm actually going to give a bit more current. I think this is probably going to draw like a fair bit of current on idle with 14 point something volts going in. Okay, 9.8 amps of idle, and we have got a massive 155 volt negative rail. Alright, so that's pretty high voltage, so let's see. So, yeah, this one FET is getting warmer than the rest of them. It just has a teeny tiny bit of warmth on it. Whereas the high sides on this bank don't have anything. There's no heat whatsoever on any of those. So that's something that's a little different between these two. Why? The gate resistor is not any different. So why would that one? I've compared all the low side drive waves, they look identical. I've compared all the high side drive waves, they look identical. I've confirmed that the pull down resistors are there, all the same. The gate resistors are there, all the same, they're all good. I've confirmed basically the continuity to the drive circuit, that's perfect. The driver board is brand new. I've confirmed that all the small green inductors on the board are good, and the source resistors that are 5 ohm, they're all good as well. So there's nothing left on here that I can see that might cause this to get a little warm. Honestly, nothing at all. Ah, wait, I think I know why that one might feel like it's getting warm. Because it's right next to this rail resistor that's getting stanky hot. Yeah, that makes perfect sense. We've got these great big resistors on the board here, which get really hot because they're sinking the rail voltage. So that's very close on the board to this, and I bet it shares. Yes, I think this FET is getting hot because it's next to this resistor. This FET warms up a tiny bit because it's next to this resistor, which is also getting hot. Cold. See, that's the thing though. This one on this side next to the resistor does stay cool. So that is curious. So why don't the ones on this side heat up when they're next to the resistor, but the ones on this side do? Maybe it's because the traces are on different things. I'm going to check the traces and see what these resistors are connected to. Because if something on the board is heating up like this resistor, which it's designed to, if right? This is really interesting. So if this resistor is for the positive rail and this resistor is for the negative rail, okay, then this resistor is for the positive rail is right next to the high side FET, which has the positive rail on it. So therefore, the leg of this resistor is going to get hot, which is in turn going to heat up the back of this high side FET. Whereas if this side is the negative voltage, negative rail voltage resistor, then this one will not be heating the center leg of this FET. It will be heating the gate and source, which you're not going to feel on the back of the FET like you would the heating of a leg. So that might make perfect sense as to why it feels like they're heating up. So is this resistor connected to the back of this FET at all? Yes, it is! That's why it's getting hot, because it's just sinking heat through the board. Fuck! Right, okay. But this side, I bet this side is the negative. Oh my god, my theory was fucking spot on! My theory was correct. So this resistor is for the negative rail, so therefore it's on legs, it's on the source, and not the back, not the drain. That's why these ones are heating up, because they're next to the resistors, which is sharing a trace on the board with them. Thank fuck for that. Thank God for that. Woo! That's awesome. This is the shit I love about amplifier repair, is when you have an issue like that you're not sure about and you figure out what it is. That feeling is absolutely fantastic, and that's why I love doing this repair stuff so much. I'm a massive problem solver. I love problem solving, and so yeah, when an issue presents itself to me like that, and we systematically look and try and work out what's causing that, and we find the issue, for me, I can't beat that feeling. That's a fucking good feeling. So, as a result, I believe we have a successful repair. Boom, boom, boosh! So now all that's left to do is to reassemble this back into the massive case that it comes in, and then do some endurance testing. But I believe that this is going to be fantastical, good going forward, and happy days. So, she's back in the case, and I've just been running this for about 10 or 15 minutes, doing some sort of lowish power endurance tests. It seems very happy. The drive waves look excellent whilst it's playing audio. It stays very cool as well. So now what's next to do is to do a higher power endurance test. I can only actually get it up to about 4.5 to 5k on my Dell server power supplies, but if it does that consistently and stays cool and does it very happy for a long period of time, then there shouldn't be any issues. You know, the issues would arise if, you know, it was doing that amount of power and there were problems. They'd arise and they'd show me and it would blow. So I'm very happy with the repair. I think this went really well, and yeah, it seems pretty good. So I'm pretty happy now to give this back to the customer and let him use it as he wishes, provided the rest of the endurance tests go well. So thank you very much for tuning in, guys. Hope you enjoyed this repair and it showed you where to look for some issues on similar boards. And don't be put off by a big amplifier. It's just a lot more things in parallel. It's the same as a smaller, but just like mirrored more of them. So don't be put off by big amps. It's just a bit scary when you're working out, you know, when you're working on the rail voltage. You just got to know safety, and you've got to know not to short things out. But yeah, take it easy, and I shall see you next time.